Okay, this is notes on 3.3, which is called function notation. And function notation is something that might be a little new to you this year. It is really a more precise way of notating functions, hence the name function notation. So it is a notation that, in a sense, names a function, states the independent variable that you're using, and gives the rule. And let me give you an example. So an example of function notation would be like f of x equals x plus 2. Notice how I read that just barely. The way we would say this in words is we say like f of x, this is f, the x is in there, is, or f of x equals x plus 2. And hold on just a moment. So a lot of people think that these parentheses right here are like multiply parentheses, but this is all just part of the notation. This is like the name of the function, and x is the variable. So if we go back, if we're thinking about functions, I have a little space up here to write. If I'm thinking about functions, imagine I have a function, and so we're going to input some values. We'll input some x values, and they go into this function machine, however you've seen a function machine look like before, and it outputs a y value, and on the inside it's going to plus 2. We'll just name this function, and we'll name it k. And so this function, when I input a number, so let's say that I input the number 5. It comes in here, I add 2 to it, and it spits out 7, right? If I input -1, it comes in here, I add 2, and it spits out +1. So this, in function notation, we would write this as k of x, because that's the variable that we are plugging in there, that we've named there. K of x equals whatever this variable you're putting in, so x, and then that rule, x plus 2. So k of x, in the past, we maybe would have just written y equals x plus 2. Like, this is the y, that's the output. But now we have a more precise language, k of x. And k of x, when we use this notation, it preserves some information, because now I can say, oh, well, k of 5, like when I input 5 into that machine, 5 plus 2, or 7, came out. And now when we look at our answer, I can see the input and the output from my answer. Here's the input was 5, and the output was 7. So it preserves a little bit more information. And one reason that we like function notation is if side by side or like simultaneously I'm working with another function, maybe its name is t, that takes x and spits out 3 times x. Whoop, that comes out. Now it makes it a little bit easier to notate like which function I'm dealing with, because this function looks like t of x equals 3x, and I could say t of -2 is 3 times -2, because it goes, the -2 comes into the function, it gets multiplied by 3 and comes out, so that equals -6. So I could say that t of -2 equals -6. So back in here, this is our function notation. So here's our example, f of x equals x plus 2. So the first thing we're going to do is we're going to evaluate some of these functions. So they gave us a function. Its name is f. It says f of x equals -4x plus 7. And we're going to evaluate it in 2 places. We're going to evaluate it when x equals 2 and when x equals -2. So basically, we're going to be plugging in 2 different inputs. So I'm just going to give myself room for both of these examples. And I'm going to say first, when, and I like to use at symbol just because at x equals 2, I'm going to plug in 2 into our variable. So f of 2, that's what we're looking for. What's the output? Equals -4 times 2 plus 7, which is -8 plus 7. So I think f of 2 equals -1. Bam, there's one of my answers. But at x equals -2, that was the second input we were going to try. When I plug that in, I'll have f of -2 equals -4 times -2 plus 7. Negative 4 times negative 2 is positive 8 plus 7. So I think f of negative 2 equals positive 15. Perfect. So those would be our two answers for this question. Let's look at number 2. This time we're going to be evaluating in 3 different places. We're going to evaluate at negative 4, we're going to evaluate at 0, and we're going to evaluate at 3. And our new function is f of x equals negative x minus 1. So at x equals negative 4 is the first one they want us to evaluate. So f of negative 4 equals negative. Okay, this is where my negative 4 is going right in here for x. So I already have that minus on the outside, but I have minus negative 4, because x is negative 4 minus 1, which is really just 4 minus 1. So f of negative 4 equals 3. Beautiful. Okay, at x equals, our next one is 0. So we're going to plug in 0. So I have f of 0 equals negative 0 minus 1. Well, negative 0 is just 0. Doesn't really matter. I think this is just negative 1. So f of 0 equals negative 1. Okay, last one. When x equals 3, I'm going to have f of 3, that's my input, equals negative 3 minus 1. So f of 3 equals negative 4. Nice. Like I said, this notation is helpful because then when someone looks at your work and they see your answer, they can say, oh, he input 3 into the equation, into the function box, whatever, and the output was negative 4. So it preserves a little bit more information. Notice that if we were to graph these on a graph, if the input and the output are like that, that means that the point on the graph, the input is x, the output is y. So it's like having the point 3, negative 4 on your graph. Okay, interpreting function notation. So we have, a lot of times this function notation will be used with some sort of like story problem. So it says, let f of t be the outside temperature t hours after 6 a.m. Explain the meaning of each statement. So f of 0 equals 58. Okay, so this is where the t is supposed to go. So that's saying that t is 0. T is supposed to be t hours after 6 a.m. So 0 hours after 6 a.m. must mean that it is 6 a.m. So I think this is saying at 6 a.m. the temperature is 58 degrees. So at 6 a.m. the temperature is 58 degrees. Nice. Okay, f of 6 equals n. So that means there's our variable that we put in. So that means t equals 6. 6 hours after 6 a.m. is at noon. So I think this is saying the temperature at noon is n degrees. I guess it's something. Temperature will be something at any given time. Okay, f of 3 is less than f of 9, so we're comparing these. This means t equals 3. This means t equals 9. So 3 hours after 6 a.m. is 9 a.m. And 9 hours after 6 a.m., let's see, so 6 hours is noon, 3 more, so this is 3 p.m. So I think this is saying that the temp at 9 a.m. is less than the temp at 3 p.m., which I can buy. Normally it warms up as the day goes on, so that makes sense. I'll buy that. Okay, solving for the independent variable. Okay, this is one that does get a little bit trippy. So they're going to ask us a different question. So they give us this function, h of x, which is 2/3 x minus 5. And then they say, find the value of x. So we're supposed to find x for which h of x equals negative 7. Remember, h of x is like the output. That's basically the y now. That's the output. So the output is negative 7. So it's saying, what do we, like the input, what input do we put in here to get negative 7 out? So it's like, what's this? What's this? What does this have to be? So that the answer is negative 7. And the way we can solve that, since h of x equals negative 7, well, here's h of x right here. Let's just make that negative 7. So I'd have negative 7 equals 2/3 x minus 5. And then I just have to go ahead and solve this. So to solve this, here's the x I'm trying to solve for. I'm going to add my 5 over first, That's going to leave me with negative 2 equals 2/3 x. And to get x by itself, I'm going to multiply both sides by the reciprocal, which is 3 over 2. That leaves me with negative 3 over here equals x. And we could double check that, so negative 3. So if I were to plug negative 3 right here, I'd have 2/3 times negative 3, which would be negative 2, minus 5, which would be negative 7. So that checks out. Okay, 6x plus 9, f of x equals 21. So I'm going to set up 21 equals 6x plus 9. All right, here's the x I'm trying to solve for. So I'm going to subtract 9 first. And that is going to leave me with 12 equals 6x. I'll divide by 2. Oh, and by 2 I mean 6. Divide by 6 on both sides. And that leaves me 2 equals x. Double check that. So if I plug a 2 in for x, that's 6 times 2 is 12, plus 9 is 21. So that checks out. Okay, last one here. G of x equals negative 1. So I have negative 1 equals negative 1/2 x plus 3. And I'm trying to figure out what that x needs to be. I'm going to subtract 3 from both sides, which leaves me with negative 4 equals negative 1/2 x. I'm going to multiply both sides by negative 2. That's going to leave me with positive 8 equals x. Should be good. So if I plug 8 in here for x, negative 1/2 of 8 is negative 4, plus 3 would be negative 1. So that checks out. Okay, we need to talk about function notation and graphs. So it says use the graph of f of x to the right to answer the following questions. So here's this graph. There's just like 4 or 5 dots on here. Okay. So each one of these dots is associated with an ordered pair xy. So like this is 3, 1. This is 4, negative 3. This is 2, negative 1. Remember, the x always comes first, so it's like over 1, down 3. And this one is 0, negative 5. And we heard the cats terrorize something in the background. Okay, so f of 1 means that my input, or my x value, is 1, and I'm trying to look for the output. So my input is 1, or my x value is 1. So I'm going to look over at 1. Here's 1 on my x value. I'm going to look up and down. Where is this dot? Okay, here it is, right there. So what's the y value for this dot? That would be negative 3. So f of 1 equals negative 3. Let's see that again in slow motion. I'm going to erase that stuff in here. Okay. F of 3. So it's saying x equals 3. So I'm going to find 3 on my x-axis. Here it is. And where's my dot that goes with that? Well, it's right up here. And the y value there is 1. Okay, so f of 3 equals 1. Okay, f of 0. So my input, or my x, is 0. Here's x is 0, looking for a dot up and down, and there's this one right here, 0, negative 5. So the y value is negative 5. Now we shouldn't ever have a problem when I go to a specific x value and then look up and down to find a dot. I shouldn't have a problem because we should be dealing with functions. And remember, functions have that property that they should never overlap right over top of each other. So that should be okay. All right, letters A, B, and C here, these second ones. These are asking that backwards question again, kind of like the ones we just solved up here, where they're actually asking us for the input, and they want to know, or they're giving us the output. So this f of x equals negative 1 is kind of saying y equals negative 1, like the output is negative 1. So I'm going to look along y equals negative 1 and find which inputs, like left and right, get us there. And I only see one point on here, it's this one right here, 2, negative 1, so that x value is 2, because that's to the right 2, and it's asking for the x this time. So I'm going to say this answer is x equals 2. Okay. How about find x when f of x equals negative 3? So I'm going to come down to 3, look across. Okay, I am hitting 2 points right here at negative 3 for f of x equals negative 3. I'm hitting this one, which is to the right 1, and this one, which is to the right 4. And that's okay because functions are like they're allowed to be side by side with each other, it's not up and down. So this actually has 2 inputs. When I input 1, I get out negative 3, and when I input 4, I get out negative 3. So this has 2 answers to it. x equals 1 and x equals 4. And then find x when f of x equals 0. So f of x equaling 0 means y equals 0. So I'm looking right along the x-axis, and I don't see any points right there. So I'm going to say this is, like, none. Maybe you could say, like, no solution. There is no input so that you would get 0 as an output because there are no lines right here, or no dots right there on 0. That's okay. Okay, last one in here. It says the function k of x equals 75x plus 100 represents the cost of adopting x kangaroos. How much does it cost to adopt 300 kangaroos? So they gave us the formula. How much does it cost to adopt 300 kangaroos? Well, then we need to figure out k of 300, which is $75 times 300 kangaroos. That's the actual adoption fee, I guess. Plus 100, that's like flat rate shipping or something. I don't know. It's going to be some big number. And how many kangaroos could we adopt if I only had $4,253? So first I'm going to figure out this 75 times 300 plus 100. And I'm going to go to a calculator. Let's see. 75 times 300 equals plus 100. So I'm getting 22,600. That's going to cost us $22,600. But we don't have nearly that much. I only have 4,253. So I'm going to figure out how many times I can fit this into 4,253. So I have 4,253 equals 75x plus 100. Well, let's just take that 100 right off because I already know I need to take that off. So I know I'm going to have to pay that. That would leave me with $40,153. And I just had to fit those 75. So I'm going to divide both sides by 75. I think we get x equals, so it's 4153 over 75. Oh, not now. Oh, I got distracted because it asked me, 4153 divided by 75. 55.37. Okay, well, we're not going to be able to buy a part of a kangaroo, so I'm going to say that we'll just be able to get 55 kangaroos. Nice. Gotta save room for money and, or like for beds and food and college and stuff or something if we're having kangaroos. Okay, that is 3.3 function notation. So big things, don't forget these parentheses do not mean multiplication. It's just notation f of -4. It's just telling you the function name and then what your input was. And then equals and then the output. It is not multiplication, so you don't have to do anything weird to that. It's just notation.